Jiga.io is a tool that has entirely transformed the way I design parts as a mechanical engineer. More about them later in the video. You've probably heard me say this in my other videos, but I can't stress it enough. Designing parts that can be manufactured and assembled is one of the most valuable skills to possess as a mechanical engineer. It's what separates a good mechanical engineer from a great mechanical engineer. And here's why. Companies are desperate for engineers who can design manufacturable parts with cost efficiency in mind. It's simple. Money talks. Let me give you a real-world example. Bob, a junior engineer, designs a CNC machine part that costs $1 per unit to manufacture. No big deal, right? But what if I said a smartphone company needs 100 million of them a year? That's $100 million spent annually just on one part. But then along comes Charlie, a senior engineer. He redesigns the part with DFMA, or design for manufacturing and assembly principles, in mind, and brings the cost down to 90 cents. Charlie just saved the company $10 million on a single component. Now multiply that by the hundreds of parts in a smartphone. Imagine the massive savings across the entire operation. That's the kind of impact that a mechanical engineer with solid DFMA skills can have. But here's the kicker. Despite the importance of DFMA, many mechanical engineers that I've worked with, some from even the top institutions and companies, don't get it. Why? Well, for one, there are literally hundreds of manufacturing processes, each with their own set of design guidelines and rules. It can be very overwhelming and virtually impossible to learn these things on your own without any practical experience. The truth is, 95% of mechanical engineers design parts on their computers without ever stepping foot into a CNC shop or seeing a plastic injection molding machine in action. With the globalization of sourcing and supply chains, you might be designing parts in San Francisco, and these parts are being made and assembled 8,000 kilometers away in Shenzhen, China. So if you've never seen the actual machines or truly understand the exact process steps and parameters that are so instrumental in bringing your designs to life, how can you expect to optimize them? So in today's video, I'm going to be talking about a dozen or so manufacturing processes that every mechanical engineer should know, and a systematic way of learning how to design parts for each of these processes. The first type of foundational manufacturing process is CNC machining. It's a subtractive manufacturing process where material is removed from typically metals and plastics to arrive at the intended shape. Three key machining processes are milling, turning, and drilling. Milling involves removing material from a workpiece using a rotating cutting tool called a mill or milling cutter. It can create complex shapes, contours, and holes by moving the cutter across the workpiece in different directions, and can be performed on flat, curved, or irregular surfaces. Milling is done on a manual or a computer numerical control or CNC milling machine. The milling machine has a tool turret that holds a number of tools like cutters and drill bits in the correct sequence. The cutting tool rotates while the workpiece is fixed to the work table. Milling is used to make a variety of things, from cylinder heads and turbine blades to medical implants and smartphone enclosures. Milling machines can achieve standard tolerances anywhere between plus minus 1/1000th to 5/1000th of an inch. With certain machines and specialized setups, tighter tolerances of 2/10,000ths of an inch are possible. Turning, on the other hand, involves rotating the workpiece while a cutting tool moves linearly along it to remove material and shape it to correct cylindrical parts such as crankshaft rods, brake rotors, bearings, musical instruments, and even baseball bats. A lathe is used for turning and again can be manual or CNC. And the third machining process that you should know about is drilling, which is pretty self-explanatory. Drilling is used to create holes in a material using a rotating cutting tool called a drill bit. Either a drill press or a CNC mill can perform drilling. The holes you see in furniture, printed circuit boards, or laptop housings are created using drilling. Some notable CNC machine brands that you probably heard of include Haas, Fanuc, DMG Mori, Akuma, and Amada. Now, to really understand DFMA for CNC machining and any other other manufacturing process, you first need to understand the exact process steps, key parameters, and constraints. So the general process steps for CNC machining is importing a CAD model provided by the mechanical engineer into computer-aided manufacture or CAM software, where the machining strategy is developed and tool paths, tool selection, cutting speeds, and feeds are defined. Next, the appropriate raw material is chosen. It could be a metal like steel or aluminum, or a plastic like ABS or polyethylene. The stock is cut to the required size and mounted to the CNC machine with clamps, a vise, or a fixture. Then the appropriate tools like end mills, drill bits, reamers, taps, and T-cutters are loaded. The machine and tools are calibrated and the tool offsets are set to ensure the correct depth and cutting locations. Finally, we get to rough machining, where larger tools are used to remove the bulk of the material. To minimize cycle time, faster cutting speeds and higher feed rates are used here. After roughing, semi-finishing cuts are made with smaller tools to further refine the part geometry. Lastly, the finishing pass is where precision machining happens. Fine tools and slower cutting speeds are used to machine the part to its final tolerances and surface finish. This step is crucial for achieving smooth surface finishes and accurate dimensions. If the part requires holes, the CNC machine drills or bores them at this stage. Tapping is done to create internal threads, and boring might be used to refine hole diameters to tight tolerances. Of course, the CNC machining process might look different for each part, but you now have a pretty good high-level understanding of the process. Now, before we continue, speaking from personal experience, sourcing quality, affordable parts fast is extremely challenging, especially when faced with all kinds of deadlines on engineering projects. That's why I highly recommend you to try out Jiga.io, who is very kindly sponsoring this part of the video. Jiga is a unique custom parts manufacturing platform that connects you with a vast network of vetted suppliers, allowing you to directly communicate your requirements to them. This means you get parts faster, cheaper, and made exactly the way you want. With Jiga, you get to build relationship with suppliers, which not only makes the process more reliable, but also simplifies even the most intricate projects. Whether you need prototype or production parts, Jiga can do it all with its CNC machining, sheet metal, 3D printing, and plastic injection molding capabilities. Their platform is insanely user-friendly. All you need to do is upload your parts and Jiga will provide a quote within hours from multiple suppliers, allowing you to compare prices and lead times to get the best deal possible. What's even better is Jiga's service is fully transparent. You can directly communicate with the supplier for DFM feedback on Jiga's website and add notes to the 3D models to let them know your requirements. Recently, I needed a last-minute custom part made for a personal project. I simply uploaded my CAD files to Jiga, and literally within minutes, I got quotes from 3 different suppliers and received the parts in under a week. Jiga is also trusted by top-tier companies like Google, NASA, and Flex, so you can be sure the quality and on-time delivery of your parts are guaranteed. So if you're looking to simplify and streamline your manufacturing sourcing and get parts much faster, definitely check out Jiga.io through the link in the description below. Now let's talk about the important parameters of CNC machining that significantly impact the accuracy, precision, and efficiency of the machining process. The ones to keep in mind are cutting speed, feed rate, and depth of cut, which govern material removal rates and surface quality. Spindle speed, tool path, and tool life affect precision and efficiency. Workpiece material, coolant application, and machine stability ensure optimal machining conditions for quality and repeatability. Keeping these parameters in mind, now let's talk about the constraints. The first constraint is, of course, tool access and reach. CNC machines rely on rotating cutting tools which can only access certain areas of a part. That's why deep cavities, narrow features, and complex internal geometries may be difficult or impossible to machine. Limit the depth of cavities to no more than 4 times the tool diameter to avoid tool deflection. If your part does have deep pockets, incorporate a 1 to 3 degree draft angle on all vertical walls to reduce tool wear and improve material removal. Design parts with shallow pockets or consider splitting complex parts into multiple components for assembly. Remember, every design element should serve a functional purpose. If it doesn't, eliminate it to reduce cost and complexity. The second constraint is CNC cutting tools are cylindrical and cannot create sharp internal corners. Therefore, you should always fillet corners with a radius of at least 1/3 the cavity depth. The third constraint is thin walls vibrate, deflect, and break under machining forces, so keep wall thicknesses to at least 0.8 millimeters for metals and 1.5 millimeters for plastics to ensure stability and avoid warping. The fourth constraint is standard CNC tools cannot create undercuts, which are simply hidden geometries that are not visible from above the part. Avoid undercuts if possible, but if they're absolutely necessary, design them with standardized clearance cuts so that off-the-shelf tools like T-slot cutters and dovetail tools can be used. The fifth constraint is non-standard hole sizes require custom tools or extra machining time, so stick to standard drill sizes and thread sizes. The sixth constraint is tighter tolerances increase machining time and cost. Apply tight tolerances only to critical features. For non-critical dimensions, use standard tolerances of ±0.05 of an inch or 0.125 millimeters or more. This reduces cost and speeds up production. The seventh constraint is small features and intricate designs are difficult to machine and require tiny tools that are prone to breaking, so avoid features smaller than 2 millimeters in size. The eighth and last constraint we'll discuss is complex geometries make it difficult to securely clamp the workpiece. Ensure there are flat surfaces or bosses for clamping. Complex parts might need to be divided into multiple setups or require custom fixtures. The second manufacturing process that every mechanical engineer should know is additive manufacturing or 3D printing. Unlike CNC machining, which is subtractive, 3D printing is an additive process where material is built up layer by layer to create a part. 3D printing offers many benefits and can create complex geometries that would be impossible or costly to produce with traditional manufacturing methods. It's a game changer for prototyping, testing, and even making production parts. Now, there are many different types of 3D printing, and I won't go into detail for every one in this video, but fused deposition modeling or FDM is the most common and affordable method. FDM printers extrude thermoplastic filament through a heated nozzle layer by layer and are widely used for prototypes, functional parts, and hobbyist projects. Some notable brands include Prusa, Raise 3D, Bamboo, MakerBot, Creality, and Ultimaker. Another popular one is stereolithography or SLA, which was the world's first printing technology. This method is more complex than FDM and uses a light source to cure liquid resin layer by layer. SLA produces high resolution, tighter tolerances, and smooth surface parts, and is often used for intricate prototypes and end-use parts, but at the same time, it's also more expensive and has a higher cycle time. Notable brands include Formlabs, Prusa, 3D Systems, Anycubic, and Peel Poly. Selective laser sintering, or SLS, is the third type that utilizes a laser to fuse powder material together layer by layer. It's popular for producing functional and durable prototypes and end-use parts for industries like automotive and aerospace. Printer brands include 3D Systems, EOS, Formlabs, Centauret, and HP. Next is multi-jet fusion, or MJF. MJF printers jet a binding agent on a bed of powdered material followed by heat to fuse the powder. It offers high-quality surface finishes and is used for prototypes and production parts. Notable brands include HP, VoxelJet, E+3D, and Farsoon Technologies. These four methods are primarily used for printing plastics. SLS might be used for printing metals as well. Direct metal laser sintering and selective laser melting are two methods for printing metal parts. Binder jetting is a less common method for printing metal and ceramic parts. In terms of precision, SLA ranks at the top and can achieve a tolerance of ±0.04 of an inch or 0.1 millimeters, followed by MJF and SLS, with FDM being the least precise at around ±0.20 of an inch or 0.5 millimeter. millimeter. However, FDM is the most cost effective in terms of making prototypes and large parts. So you ultimately have to pick and choose which method to use based on your design needs. Common 3D printing plastics include ABS, PLA, polycarbonate, nylon, and TPU. Metals include aluminum, stainless steel, titanium, and Inconel. The general process steps for 3D printing are first slicing the CAD model into thin layers and saving it as an STL file. Each layer is a 2D representation of the part. Next, the raw material, whether plastic filament, metal powder, or resin, is loaded into the printer. The printer then does its thing, and the total print time will vary based on printer settings and type, part size, and infill density. Lastly, any support structures and rafts are removed, and the part can be sanded and polished if necessary. Now, there are several parameters to keep in mind when designing 3D printed parts. Higher infill provides strength but uses more material and takes longer to print. Printing speed affects the time it takes to print the part and can impact surface quality. Slower speeds often result in better quality but takes more time. The nozzle temperature and print bed must be carefully controlled for good material flow and adhesion between layers. Layer height determines the resolution and surface finish of the part. Smaller layer heights give finer detail but increase printing time. Then there's support structures for overhangs, undercuts, and complex geometries. Supports are often needed to prevent sagging or distortion during printing. As for the constraints to consider, the orientation of the part during printing is very important and affects the surface finish, strength, and print time. Try to orient the part so that critical surfaces are printed in the XY plane, where most 3D printers offer the highest precision. Maybe you don't care about precision and just want to minimize print time. In that case, play around with different orientations, print speed, and infill density. Next is material shrinkage. Certain materials, especially metals and some plastics, shrink slightly as they cool and solidify, so keep this in mind when designing. The third constraint is complex internal structures. While 3D printing allows for the creation of internal channels and voids, they can be very challenging to clean and inspect, so ensure they're accessible or include escape holes for removing any trapped powder, uncured resin, or support material. The fourth constraint is thin walls, which are prone to warping. Keep wall thicknesses above 0.8 millimeters for plastics and 1 millimeter for metals to ensure part stability and printability. The last constraint is surface finish. The surface finish of 3D printed parts is often rough, particularly in FDM printing, where visible layer lines are present. Plan for post-processing like sanding, polishing, or coating if surface finish is critical, or opt for technologies like SLA or SLS for smoother surfaces. Next up is injection molding, which is a formative manufacturing process and where material is forced into taking on a certain shape. No material is removed. It's the go-to method for the mass production of parts made out of plastic materials like ABS, polypropylene, polycarbonate, nylon, and polyethylene. Injection molding works by injecting molten material into a mold cavity where it cools and solidifies into the final part shape. Injection molding is used to produce high volume, complex, and detailed parts, including Legos, smartphone enclosures, dashboard panels, and syringes, but can also be used for prototyping. Its process steps includes firstly clamping the two halves of the mold together. The mold is commonly fabricated out of hardened steel or aluminum. The half of the mold that shapes the internal features of the part and contains the ejector system that pushes the part out is called the core. The other half of the mold is called the cavity that forms the exterior or cosmetic surfaces of the part. The second step is injection of the molten plastic material into the mold cavity at high pressure using a screw or ram injector. Next, cooling and solidification of the material into the shape of the cavity occurs. Then the fourth step is ejection of the cooled part where the mold opens and the ejector pins push the part out. Some parts might require post-processing like trimming flash, polishing, or painting. Now let's move into the critical parameters of injection molding. First is injection pressure, which controls the flow of the molten material into the mold. Higher pressures allow for more intricate details but can cause flashing or deformation. Second is temperature. The material must be heated to the correct melting point. Too low of a temperature leads to incomplete fills called short shots, while too high of a temperature can degrade the material. Third is cycle time, the time it takes for clamping, injection, cooling, and ejection. Fourth is clamping force, which ensures the mold stays closed during injection. Higher forces are needed for larger parts and those with complex geometries. An adequate clamping force can result in flashes and poor geometrical precision. Finally, cooling time affects the final quality of the part. Insufficient cooling can result in warping or shrinkage. Now, in terms of constraints, here's how you can apply DFMA principles to address them. The first constraint is uneven or thick walls can cause warping, sink marks, and voids. Keep wall thicknesses uniform to ensure even cooling. Aim for 1 to 4 millimeter thickness for most plastics. The second constraint is parts without draft angles will stick to the mold, so apply a draft angle of at least 1 to 2 degrees on all vertical walls to facilitate ejection. The third constraint is features that prevent the part from being ejected straight out of the mold create undercuts, making ejection difficult. Avoid undercuts when possible, but if it's necessary, choose the parting line wisely, which is just the line where the two halves of the mold meet. You'll also want to modify your designs to incorporate side actions, bump offs, and lifters to handle undercuts. The third constraint is plastic shrinks as it cools, leading to dimensional inaccuracies. Therefore, account for material-specific shrinkage rates, typically between 0.5 to 2%, and add ribs or gussets to strengthen thin walls while minimizing material usage. The fourth constraint is sharp corners create stress concentration points and can lead to cracking. Incorporate fillets with a minimum radius of 0.5 millimeter to reduce stress and allow for easier flow of material. The fifth constraint is visible seams, aka parting lines, are left where the mold halves meet, so design parts with clear parting lines. Ideally in non-visible areas of the part to hide any imperfections from the seams. The next constraint is thin-walled bosses can crack or sink during molding, so use rounded bosses with sufficient wall thicknesses and avoid creating thin-walled areas around holes. Last but not least, complex flow paths can lead to short shots or well lines where molten material meets. Ensure proper locations of gates, which is where material enters the mold, and avoid ununiform wall thickness. If your design has holes, it's very likely that weld lines are unavoidable, so if cosmetics matter a lot, consider machining part features like holes into the part after injection molding has completed. That brings us to the third essential manufacturing process, and it's another formative process like injection molding, sheet metal forming. Sheet metal forming can also involve subtractive processes like laser cutting or punching, where material is removed to create holes or cutouts. However, sheet metal forming is more about forming rather than removing material like CNC machining. Sheet metal forming involves bending, stretching, or otherwise shaping metal sheets into the desired form. There are tons of sheet metal forming processes, so try and learn as many as you can. A good one to know is bending, which is pretty straightforward. The metal sheet deforms by applying force to it at an angle on a press brake or hydraulic press with a punch and a die. Next, stamping uses a stamping press that presses a sheet into a die to form a part and actually encompasses a handful of forming processes like punching, blanking, coining, and embossing. Then there's deep drawing, where the sheet is drawn into a die to form a deep hollow shape such as a cup or a can. Think kitchen sinks, soda cans, and gas tanks. Next is stretch forming, which is similar to bending, but is commonly used to make components that require a larger bend radius like aircraft fuselage and wing components and car door panels. Spinning is used to make axis-symmetric parts by rotating a flat metal disc or tube against a forming tool on a spinning lathe. Think vases, rocket noses, and scuba tanks. Roll forming, on the other hand, is leveraged to make lawn products like gutters as well as tubes and pipes in automotive exhaust and HVAC systems, metal roofing panels, and metal housings in refrigerators and ovens. Common sheet metal materials include steel, aluminum, copper, and titanium. Now, the process steps for sheet metal forming will vary based on part complexity, but generally the sheet metal is placed onto a die which shapes it through processes like bending, stretching, or stamping. Tools like punches or press brakes brakes are used. The metal is pressed or stretched to its final shape using equipment like hydraulic presses or mechanical stamping machines. After forming, excess material is trimmed and holes may be punched or laser cut to precise locations. Additional secondary operations like hemming, embossing, or welding might be performed, and surface finishing processes like painting, anodizing, or powder coating might be applied to improve cosmetics and enhance material properties. The key parameters that you should think about when designing sheet metal parts are bend radius, material thickness, tooling clearance, and forming speed and pressure. The constraints include bend radius, which is the minimum radius the sheet can be bent without cracking. Typically, it should be no less than the sheet's thickness. Then there's spring back. All sheet metal will spring back slightly after bending due to elastic and plastic deformation. To counter this, overbend parts slightly or adjust tooling. Spring back depends on many variables but can be predicted with reasonable accuracy using K-factors, spring back factors, elastic modulus, and yield strength. Based on my experience, mechanical engineers can design sheet metal parts with appropriate compensation for spring back. The manufacturer's expertise will then fine-tune the process to meet your specifications. Next is material thickness. Thicker sheets are stronger but harder to form, and thinner sheets can be shaped more easily but lack strength. You should also avoid drastic changes in material thickness that can lead to stress concentrations and defects such as cambering. The fourth constraint is hole placement. Sheet metal is prone to tearing or distorting when there are holes, so keep them at least 2 to 3 times the material thickness away from the edge of the sheet. The next constraint applies to deep drawing. Limit the draw ratio, which is the height to diameter ratio, to less than 2 to 1 to avoid tearing or wrinkling, and use gradual transitions for complex geometries. Constraint number 6 is flanges and tabs are prone to buckling, so the length of them should be at least 2 times the sheet thickness. Another formative manufacturing process very similar to injection molding is casting, where liquid material is poured into a mold and allowed to solidify, forming the desired shape. Casting is especially suitable for producing high volume parts with complex geometries that would be difficult to machine. There are many different types of casting, and I like to categorize them based on mold type. Either an expendable mold that is destroyed or altered during the removal of the cast part for low to medium production volumes, or a permanent mold that is reused multiple times. It's generally used for higher production volumes and parts that can be easily removed from the mold. Expendable mold casting includes sand casting, where a pattern is placed in a sand mold, the sand is compacted around it, and the pattern is then removed, leaving a cavity for the molten metal. The sand mold is destroyed or broken to remove the casting. Sand casting is used to make things like engine blocks, cylinder heads, and pump housings. Another one is investment or lost wax casting, where a wax pattern is coated with a ceramic shell, which is then heated to remove the wax and harden the shell. The shell is destroyed to remove the finished part. This method is used for intricate and high precision parts. Permanent mold casting includes die casting, where molten metal is injected under high pressure into a reusable steel mold. The mold is designed to be used repeatedly, and the castings are removed after solidification. Another is centrifugal casting, where molten metal is poured into a rotating permanent mold. The centrifugal force helps to distribute the metal to create a high quality casting. This process is used to make axisymmetric parts like pipes, flywheels, cylinder liners, and jet engine compressor cases. Casting materials include steel, aluminum, bronze, brass, and ceramics. The process steps of casting begins with creating a pattern and then making the mold with the pattern. The molten material is poured in the mold cavity through the sprue and runner system, and then it cools and solidifies within the mold. After the casting has solidified, the mold is either broken or opened to remove the part. The key parameters of casting are pouring temperature, cooling rate, mold material, cycle time, and material flow. One constraint to be aware of is, of course, shrinkage. Design parts to be slightly larger to compensate for shrinkage. Another is wall thickness. Larger variations in wall thickness can cause uneven cooling and lead to defects like warping or cracks, so keep walls as uniform as possible. Third is draft angles. Adding a slight taper to the part's vertical walls, typically between 1 to 3 degrees, helps with mold release. Fourth is sharp corners. Sharp internal corners are stress concentrators and can cause cracking during cooling. Always round off corners or fillet them to a reasonable radius. Fifth is section thickness. Thin sections are prone to defects like incomplete filling or rapid cooling, so avoid walls thinner than 3 millimeters for metals. Thicker sections will require risers to feed material during shrinkage. Sixth is undercuts. Similar to CNC machining and injection molding, casting can struggle with undercuts, as these can trap the part in the mold. Minimize or eliminate undercuts, or design the mold to include cores to manage complex internal geometries. So to summarize, we covered 3 essential categories of manufacturing processes: subtractive, additive, and formative, along with several key processes within each. But the world of manufacturing is vast and includes a lot more, such as joining processes like welding, brazing, soldering, adhesive bonding, and riveting, as well as surface finishing techniques like anodizing, PVD, CVD, polishing, and electroplating that I'll likely cover in a future video. For mechanical engineers, knowing about these processes is a good start, but it's not nearly enough. It's critical to tie DFMA principles to the process steps, parameters, and constraints of each manufacturing process to elevate your designs and engineering expertise. This will make you an irreplaceable mechanical engineer who can impact a company or the world through practical design. Alright guys, that's it for today. As always, thank you so much for watching, and if you found this video helpful, be sure to check out my video here where I talk about how I would relearn mechanical engineering if I could start over, and I'll see you in the next one. Peace.